with power series. So the idea is that in Calc 1 you did learn ways to calculate limits of things like this, x times sine 1 over x, use indeterminate forms or whatever, different techniques. And what we're saying in this chapter, this section is, hey, well you could also just use the power series and it becomes very algebraic and you don't have to use L'Hopital's rule and things like that. Sometimes it's a little bit more work, but it's just interesting that we can do this. So we can just take the function and replace it with its power series, then the limit can be computed. So we're just going to replace sine of 1 over x in here with its equivalent power series. So the power series for sine of x is right there. It's all the odd powers of e to the x with a switch thrown in. And maybe I'll put e to the x up on the board because e to the x is such an important one. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. If we wrote it in summation notation, it would be x to the k over k factorial when k starts at 0. So that is the exponential function, the most important one. And we notice that sine is just the odd powers, but you put in a switch. Cosine is the even powers, but you put in a switch. So in this particular example, we have sine of 1 over x. We have to do a little substitution. So we just have to turn all of these x's into 1 over x. So 1 over x, this is going to be 1 over 3 factorial times x cubed. This is going to be 1 over 5 factorial times x to the 5th. And maybe we'll go one more term. This will be 1 over 7 factorial times x to the 7th plus etc. So we have that. Now, whenever we do a substitution, we also need to keep in mind the interval of convergence. And so this interval up here is for sine of x, and if we replace x with 1 over x, we would do the same thing with this interval of convergence. It's going to be fine. We'll focus on this part down here first, and then we can talk about it. So we're going to distribute this x here, right? We're going to distribute the x across, and when this x gets distributed across, we'll have a cancellation with each of these denominators. So we have that. And the limit is as x goes to infinity. So what is true about all those little fractions? What happens for all these when x goes to infinity? Yeah, they're all going to go to 0 because the denominator is getting infinitely large. So these all go to 0, and our limit is 1. So let's talk about this interval of convergence for a minute. If we think about replacing x with 1 over x, the original interval of convergence there says x can be any real number, correct? Any real number is what that says. And if we replace x with 1 over x, if x is any real number, 1 over x is also a real number except for one value of 0. Right? So if we have x being any real number and then we take its reciprocal, the reciprocal of any real number is still a real number except in one case, and that's when x is 0. So we can't let x be 0. So the interval of convergence here will be all real numbers except for x not equal to 0. So So that will be true for all real numbers except x equals to 0. If we're letting x go to infinity, totally fine. All right, let's go to the next slide. Same idea here. We have a limit that is an indeterminate form. If you plug in the 1, you get 0 over 0. So your natural technique would be, if you're in Calc 1, you do L'Hopital's rule. Here, we're just going to be clever and say, yeah, L'Hopital's rule is slick, but using power series is slicker. So we have this power series for natural log of x. So we're going to just replace it into the denominator. And really, when you use power series to evaluate these limits, it's just a question of being careful with algebra usually. This goes on forever and ever. And what we see is that we're going to cancel out x minus 1 across the board. So we're going to divide x minus 1 into the numerator, divide x minus 1 into the denominator, and then we're going to be left with a pretty straightforward limit evaluation. So x minus 1 goes into x minus 1 once. It goes in there once, goes in there once, and we have 1 left over. So x minus 1 divided by 2, and then plus x minus 1 squared divided by 3, etc. Make sure we put the dots. The dots are there. It's an infinite series. And then what we see is that each of these terms in the denominator, other than the first, these are all going to go to 0. Because the numerator is going to 0. As x goes to 1, 1 minus x goes to 0. 0 divided by anything that's non-zero will be 0. And so we get a limit of 1 here also. Okay. Then, any questions on that one? It really becomes an algebra exercise. We do a direct substitution, and then we do a little algebra, and then we evaluate the limit. So in a similar way down here, e to the 1 over x, well, there's e to the x right there, so we're going to replace all the x's with 1 over x. And when we replace the x's with 1 over x, we have that situation. So it's very similar to the one we looked at a moment ago. We do our algebra step here. The algebra step simply involves distributing that x. So we distribute the x here. Oh, whoops, I forgot a minus 1 over here, didn't I? This is e to the 1 over x minus 1. So there's the infinite series there for e to the 1 over x, but then we subtract off 1. So that's going to go away. This one and this one subtract each other away. And so then when the x distributes, we are going to have x goes to 1 over x, we get a 1. X goes to this one, and we get 1 over 2 factorial times x. And then we get 1 over 3 factorial times x squared, plus etc. And once again, we see that as x goes to infinity, we have all these terms, all these terms over here are going to go to 0. So our overall limit, it's 1 again. Lots of 1s. So if we have the power series for a particular function, we can just replace the function with its power series. Yeah?
What about its interval?
So interval convergence, same idea here. This is true for any real number. So x is a real number here. It's an element of the reals. And once again, we did a substitution of 1 over x. So this power series is going to be true for any real number as long as x is not equal to 0. That will be true. For any real any non-zero real. 0 causes division by 0. Okay, so let's do a couple that are a little more interesting than just evaluating limits. So the same is true for integration. As long as these limits of integration, as long as this interval fits in here, you can replace any function with its power series. This is a very hard function to integrate. We don't even know how to integrate that. Square root of 1 plus x to the 4th. We might be able to do a trig sub type of thing and try to get at it, but it's not going to be that easy in this particular case. It will not be that trivial. So this is a binomial. And here is the binomial expansion for the root of 1 plus x. So we already know that. We calculated that last week. So what we could do here is replace this binomial. So we'll go from 0 to 0.2. And we're going to replace this binomial with the series expansion. The only difference is that we have to replace x with x to the 4th. So we're going to do this. And then we're going to have x to the 8th over 8. And that's a minus sign right there. And then we're going to have x to the, bless you, x to the 12 divided by 16 minus etc. dx. And if we think about the interval of convergence, when we replace x with x to the 4th, I think doing it graphically, visualizing what x to the 4th looks like, y equals x to the 4th is a super flat parabolic-ish looking thing. And we want that value to be between -1 and 1. And if we look at the x-axis, that puts us between -1 and 1. So -1, and let me put my greens a little bit smarterly positioned. Let's see, so red is 1. I just need to line up my greens so that they're right there and right there. So what we see on the x-axis is if we go from -1 to 1, including the endpoints, the y values for y equals x to the 4th will be in between -1 and 1 on the y-axis. So the interval of convergence is not changing, in other words. Interval of convergence will be the same when you replace x with x to the 4th. It'll be the same x's. So now we do our integration. This is a polynomial. We integrate term by term. So x to the 5th, this is going to be x to the 5th. We divide by 5, so that gives us 10. This is x to the 9th. We divide by 9. 9 times 8 is 72. We'll go one more term, x to the 13th. I'm not going to multiply those together. We don't care. And this goes from 0 to 0.2. Okay. Now we plug in our upper limit. We get 0.2 plus 0.2 to the 5th divided by 10 minus 0.2 to the 9th divided by 72 plus 0.2 to the 13th divided by 13 times 16 minus etc. And then we subtract off evaluated at 0, but when you evaluate it at 0, you get 0. So minus 0 here, if you want. Now this is this is turned into an alternating series after this first term. Right? The rest of this is an alternating series, and the question said, let's estimate the value of this integral so that we have an accuracy less than 10 to the -4th. 10 to the -5, I switched it. So with an alternating series, we just look for the first term that's less than 10 to the -5. So if we go over and just do a little calculation, we'll be able to figure out the first term in this infinite series that has a value less than 10 to the negative 5. So 10 raised to the negative 5, just to get a look at it. And then let's go with 0.2 raised to the 5th power divided by 10. Is that one small enough? Is this less than that?
No.
Not yet. So that's a 3 in the 5th position. That's a 1. So we kind of know that the next one's going to do it. If we go 0.2 to the 9th, and then we divide it by 72.
Yep.
Yeah, that thing is definitely less. So we have that this is the first term that's less than 10 to the negative 5. So if that's the first term that's less than 10 to the negative 5, that's less than 10 to the negative 5. That means we add everything in front of it. So we're going to add those. So our estimation will be 0.2 plus 0.2 to the 5th divided by 10. So we just type that into our calculator and get that estimation, and that will be our answer. So we just have 0.2 plus 0.2 raised to the 5th divided by 10. So there is our estimation. I can just highlight these instead of getting them. I feel like that's not going to work. Yeek. LaTeX, we don't need you. Not now. So we'll just do that. You over there, and then we're good. All right, any questions on how that works with the estimation? So we're just using our, bless you, our alternating series remainder. So remember that with an alternating series, it's the one time that we really do use the remainder. And if you add up a bunch of terms, the first term you don't use is the error estimate for the addition of all the terms in front. So for us in this particular case, this term is the error estimate of everything in front of it added together. This would be the error estimate for all those terms added up. So for alternating series, it's pretty straightforward. You look at the first unused term. Let's try one more of these. So we have this integral here. We are going to do a similar type of thing. We're going to take the power series for that function. This interval falls within that interval. So we can just switch this function with its power series. The power series and the function are equivalent when you're working within the interval of convergence. Wherever you see a power series, you can replace it with the function, or wherever you see the function, you can replace it with its power series if you're within the interval of convergence. So we have that. Notice this is just the odd powers, exactly like sine. So sine is the odd powers of e to the x with a switch thrown in. Inverse tangent is also the odd powers of e to the x with a switch tossed in. With one extra little thing, we just erase the factorials. So tangent and sine, and one thing that we've actually already seen this semester is that if you looked at the tangent function, inverse tangent. If you look at the inverse tangent function, the linear approximation for the inverse tangent function is x, same as for sine. If you graph the sine function, the linear approximation at the origin is also x, which now makes a lot of sense when you look at their power series. They actually have the same exact first term, which means they have the same exact tangent line at 0. So here we're going to plop through, we're going to do our regular power rule business. And when we do our power rule stuff, in this particular case, we end up with that from 0 to 0.3, 0.35. So this is going to be 0.35 squared over 2 minus 0.35 to the 4th over 12 plus 0.35 to the 6th over 30. 0.35 to the 8 over 56 plus etc. And then we subtract off 0. We don't care about the subtraction of 0. That's not going to change anything. And so we're in the same position we just were. We need to know where is the first term that is less than the threshold that was given, which was 10 to the negative 5. So we're going to do the same type of thing here. Let's try to find, let's just start with 0.35 raised to the 6th power, since I can see that one, divided by 30. Is that one less? We have 4 zeros and a 1. Here we have 1, 2, 3, 4 zeros and a 6. So not quite enough. So if we go to 8, and then down here, change that to a 56. Voila. 1, 2, 3, 4, 5 zeros versus 4. That's definitely less. So that is our error estimate for everything in front of it. So this term with the 8th power, this is the first term that's less than 10 to the negative 5. So your approximation is going to be the sum of these 3 terms. And I can add those up during the break. So whatever that adds up to, that is our approximation for this definite integral, and we will be within 10 to the negative 5 of the actual answer. Yeah?
I saw that you kind of like show us that like tangent, the inverse of tangent of x is equal to all those things. Would that be given to us, or is that something that we have to recognize and then?
So I'm going to tell you 5 power series today that you have to memorize for the test. One of them is e to the x. One of them is the geometric series. One of them is inverse tangent of x. One, I already lost track. I'm going to write them on the board in a minute.
Sine?
Yeah, I forget if I'm going to do sine or cosine. I have to look at my notes. But yeah, for sure, e to the x geometric series, binomial, and inverse tangent. But then there's one more. I gotta look it up. I don't want to tell you one thing and give you the wrong one. Okay, so last thing, just kind of an anomaly or a side note, and we talked about this a little bit. If you wanted to find an infinite series for different irrational numbers, all you do is plug in the constant that you need. So here the exponent on e is 1/2. That's the constant we would plug in for this x. And we could write, if we were so inclined, if we wanted to, we could say square root of e is 1 plus, we're plugging in x equals 1/2. So if we just plug this in across the board, this is exactly equal to e to the 1/2. So that infinite series converges to the square root of e.
Where does the half come from?
Because a root
Right.
turns into an e to the half. So e to the 1/2 is square root of e. So if we take e to the x and replace x with 1/2 all the way through, that is an infinite series for the square root of e.
So we're only plugging the, so we're substituting also the x by the power of e?
So when we look at e to the x. So e to the x is this expansion.
Right.
So if we wanted an expansion for e to the half, then we would replace all those with 1/2.
Okay, gotcha.
If we had e to the 3,
Then
we
you
would
plug in
replace
those three.
all those with a 3.
Okay.
Yeah, so whatever the corresponding x value is, if we change all those to that constant, then we have a power, not a power series, an infinite series for that number. So similarly, sine of 1 radian, if we wanted an infinite series for sine of 1 radian, all we do is replace all the x's with a 1. So if we come on through, that is the expansion or the infinite series version of sine of 1. So this is the expansion for sine x. If you want sine of 1, you would just put in a 1 right there. Make sense? So you can get an infinite series for any, kind of oddball thing you want, really. Sine of 1, sine of whatever. Okay, so that's it. We're done with the hardest chapter. Any questions on any of these examples that we looked at? So test will be Thursday, and we'll just spend the rest of the day doing review problems. So the review exercise is here. We'll start with that. And what I am going to do is add. I was coming up with the answers for all of these, and I'm going to just, down here, I'm just going to have all the answers, so just in case we don't get to all of them, you'll at least have the answers so you can work on them between now and Thursday. Yeah?
It's not like a question, but just kind of like review chapter 11. So 11.1 is just basically finding approximations, so finding the relatives, plugging the a's, and then that's when you'll do the form of the f of a plus the first derivative times x minus a, and then just keep going, and then dividing by the factorials 2, 3, 4.
So those are the Taylor polynomials. So the Taylor polynomials are functions, they're polynomials, and they go, we did a lot of linear and quadratic, and then we did some that were 4th and 5th degree polynomials. So those are approximations. Taylor polynomial is an approximating polynomial. That polynomial approximates the function that you built it from. So if we tried to get an approximation for sine, we took the derivatives of sine, and then we plugged it into what you just described, that expansion.
Okay.
Yeah. Okay, so let's take a look at some of these different examples. So we probably won't have time to do all of them, so we have to just sort of pick and choose. So we'll do this one, and then maybe, we'll just decide as we go. So when a biologist begins to study a colony of prairie dogs, has a population of 260. So the initial population, P sub 0, is 260. Regular measurements reveal that each month the prairie dog population increases by 1%. So P sub 1 is going to be this 260 plus 1% of 260. Everyone okay with that? And if you wanted to write this more concisely, you could factor the 260 to the front and write that as 260 times 1.01. Because in front here you can imagine it as 1 times 260. So if you factor out the 260, you add those two coefficients together, 1 plus 0.01 is 1.01. Okay, P sub 2 is going to be P sub 1. Okay, it's the new population, but then we have to bump it by 1%, so plus 0.01 0.01 multiplied by that. And so it's increasing. So we've got this new baseline percent, this new baseline population. That's where we're starting, but then a month later, we have to multiply that by 0.01, and we get to that. Okay, so now let's be careful. Let's factor again. So this is 1 times all that. And when we look at this, we see, oh, that's common. So we can factor that to the front, if you will. So 260 times 1.01, that's coming to the front. And we're left with 1 plus 0.01. Oh, that gives us 260 times 1.01 squared. Everyone following this factorization? So here we factored out 260, that went right there. Add the coefficients, same idea here. Factor out the 260 times 1.01, that comes to the front. You add what's left, but that matches what's already there, so you end up with the square. And you can see what's happening. P sub n will equal, what do you think? The initial population times 1.01 to the n. That's going to be our population after n months. Okay, so find the first times in the first 5 terms in the sequence. First 5 terms in the sequence, we found 3. You can keep doing this. 260, 1.01 to the third, 260, 1.01 to the fourth. Right, it's going to ratchet up the exponent by 1 each time. And then this is the general form. So if we want the estimate of the population after 12 months, we are looking for P sub 12. That's the population after 12 months, 1 year. That means we are going to plug a 12 in right there. We're going to type that into our calculator. And what was the animal we were dealing with? Prairie dogs. We are going to have this many prairie dogs.
293.
293 prairie dogs after a year. We began with 260 and feels like in real life they increase faster than that. Well, I guess 1% is a pretty slow growth rate. Not maybe, I don't know if that's accurate or not. Rabbits, we know, are faster than 1%. Rabbits are faster. Okay, let's take a look at this next one. So log limit process. So make sure you can do the log limit process. You should know how to do the shortcut. You should already see the answer to this one. The answer to this one is e to the ab, so e to the 6. You should already see that. Yep.
If we were asked this on the test, would we have to prove it, or could we just put in the shorthand for the...
You do have to use that process. So it's going to ask you to use the process, but knowing what the answer is should make it easier. But yeah, if now in a case, if you had to find the limit of one of these and you could use the shortcut, if it didn't say use the log limit process, you could go with the shortcut. But if it doesn't, if it asks you to use the log limit process, then you need to do the work. So let's do one of these. We'll do this one. So remember that we sort of build a function first. And I'm going to switch it to x's. You don't have to. So we have that. There's our function. So we convert it over to a continuous function. When you're thinking in your mind of this, you should be thinking of just a splattering of dots. Right? That's a discrete function. It's a sequence. So it's a splattering of dots. This is now a continuous function, smooth. You know, we don't know what it's doing yet. We have to see if it has a limit. And then we take the natural log of both sides. And when we take the natural log of the right-hand side, we pop the exponent down as a coefficient. Okay, now our whole goal is to find the limit. So next step, we take the limit of both sides. And on the left-hand side, when we take the limit, we move it inside the log. The log function is a continuous function, and we have a property that says the limit symbol can move inside of continuous functions. You can move inside the parentheses or wherever. You can move inside the function. So log is continuous, so the limit can move to the inside. And then over on the right-hand side, we want to take the limit as x goes to infinity. And we kind of know what we're trying to get at. We're trying to get a L'Hopital on the right-hand side. And so when I look over here, I see that as x goes to infinity, this log piece goes to 0. 3 over x goes to 0, 1 plus 0 is 1, log of 1 is 0. And so this part over here, though, 2x, that's infinite. So we want to manipulate this, and the way we manipulate it is to move it into the denominator. So we're going to move 1 over 2x down into the denominator like that. Now technically you really only need to move the x down. It feels like people tend to get a little tangled up in that though, so it's totally your choice. You can move the whole 2x down, but technically you really only need to move the x down, and you could leave the 2 out in front if you wanted. The algebra, it's totally up to you. As long as you can manage the algebra, it's totally fine either way. Okay, so now we have a L'Hopital setup. We have a 0 divided by 0, so we are going to apply L'Hopital's rule. That says take the derivative of the top, take the derivative of the bottom, and reevaluate the limit. Derivative of top, it's a log. The derivative of log is 1 over the inside. So derivative of any log, 1 over the inside, multiplied by the derivative of the inside. The derivative of the inside, derivative of 0 is 1. Actually, I said that backwards. The derivative of 1 is 0. And then when we differentiate this, we're thinking of that as 3x to the negative 1. So when you take the derivative, you get negative 3x to the negative 2. So negative 3 divided by x squared. And then down below, you're going to think of that as, bless you, 2x to the negative 1. So if you're differentiating that, negative 2x to the negative 2. So bring the power down, subtract 1. Let's see. There's something else that has to happen. What is the other thing that has to happen?
Take the derivative of the inside.
Right. So we have to use the reverse chain rule, or the chain rule when we're differentiating. We're differentiating, not integrating. So the derivative, the negative 1 comes down, we subtract 1 from the exponent, then we have to multiply by the derivative of the inside. That's the regular chain rule. So power down, subtract 1, multiply by the derivative of the inside. So this piece becomes negative 2 over 2x quantity to the negative 2, and if we simplify this,
Could it be 2x?
this would be positive 2 in the denominator though. When we move it to the denominator, that sign changes. So this is going to be 4x squared, which will be minus 1 over 2x squared. Like that. There's an easier way to take that derivative, but I just realized I made it a little harder than I needed to. So if we have 1 over 2x, can't we rewrite this as 1/2 times 1 over x? Which is 1/2 times x to the negative 1. And when you differentiate this right here, you could say, oh, the half is a constant. And then you do the minus, subtract 1, and this is multiplication. So this will be negative 1 over 2x squared. That's maybe a little easier to do the derivative that way. And we get the same thing, of course. Okay, so that goes in the denominator. Negative 1 divided by 2x squared. All right, so let's simplify that. So we have limit. We'll leave, we're going to turn everything into multiplication in the numerator. So that's there. That's being multiplied by this, which is negative 3 over x squared. Now this is in the denominator. Dividing by a fraction, you multiply by the reciprocal. So if we flip it over, we're going to get negative 2x squared divided by 1. All right, so when all is said and done, these x squareds are canceling. And we are left with positive 6 in the numerator, 1 plus 3 over x in the denominator. And now we're ready to reevaluate that limit. As x goes to infinity, 3 over x goes to 0. This overall limit becomes 6. We now have a left side that's equal to that and a right side that's equal to that. Limit of y is what our goal is. So therefore, the limit of y as x goes to infinity is e to the 6. So that's how to do the log limit process.
I have a question.
Yeah,
Can you look at the other question? I have a question about that.
this one?
Yeah, so is that not in the parentheses? Can we divide all the terms by n in that, or would it work in this case?
You can divide all the terms by n, but it's not going to help us. We're still going to have an indeterminate form. The indeterminate form that we will have is 1 to the infinity. So if you did this, which you are allowed to do this, you could do that. This is not going to help us, though. That's still going to be indeterminate. As n goes to infinity, we still will have 1 to the infinity. So the trick is going to be actually to flip it. We want to flip it so that we can then, come on. Oh, you gotta be slow. So if we flip this, and we make it n minus 3 over n, then that gets raised to the minus 4n. Now we're getting closer. Now we can distribute the n into the numerator, and we'll be left with 1 minus 3 over n, and all that's raised to the negative 4n. And so this is going to go to e raised to what power? 12. Negative 3 is the a, and b is negative 4, so this will go to e to the 12. So that would be the shortcut way to do it. And if you guys work on it using the log limit process, of course that's what you should end up with, e to the 12. E to the 12. Any questions on log limit process? All right. Limits, just basic limits here. What is that top limit? Everyone agree 0? So it's a geometric property. If you have a number that's between negative 1 and 1, so its magnitude is less than 1, and you start multiplying it by itself, 0.2 times 0.2 is 0.04. So if you take a number under 1 and you start multiplying it by itself repeatedly, it gets closer and closer and closer and closer to 0. Now because this is negative, it will approach 0, but it's going to oscillate. It's going to go positive, negative, but it's going to be squeezing down on 0. So the limit of this will be 0 as n goes to infinity. How about this one? Infinity? Because here we have that same geometric property. The base is 3 and change, And if you take a number that's above 1, 3.14, multiply it by itself, 3 times 3 is 9, 9 times 3 is 27. This is going to go to infinity as n goes to infinity. So that's just that geometric rule.
Again, another way to think about it is that it's a constant raised to the power to infinity, which it will just be infinity since it is a constant. Or
Well, here, this is a constant raised to infinity. Depends on what the constant is. So if the constant that's raised to infinity is less than 1, like if you take something like 1/10 and you raise that to n and then take the limit as n goes to infinity,
yeah, the approach is the same.
that's going to go to 0. But if you take the limit of a constant that's larger than 1, so something like 4, that's going to go to infinity. So bigger than 1, infinity, less than 1, 0. And if the constant were 1, what would happen? So if you have 1 to the n, limit as n goes to infinity, that limit is 1. Because it's 1 times 1 times 1 times 1 times 1. Different than 1 plus 1 plus 1 plus 1 plus 1. Right? If you turn that into a series, if you have this, that is infinite. Because that's adding 1 to itself a million times or more.
So here we're saying that limit as n approaches infinity, 1 to the n is 1, but in the previous case we said 1 to the infinity is indeterminate.
So, where did we say it was indeterminate?
Like in the previous question,
So that was an indeterminate form. The indeterminate form doesn't say the base is 1, it says the limit of the base is 1. So when we look, great question. So when we look right here, when we look at the limit of this is 1, and so when you take the limit, that is what's indeterminate. We write it like this. We do not mean that the base is 1. This means that the base approaches 1. And so what we see with this indeterminate form, so 1 to the infinity is not indeterminate. So 1 to the n, yeah, we've got to be careful how you, so like if we did this, and then take the limit as n goes to infinity, this is not indeterminate. That will be 1. Because the base is 1. So if the base approaches 1, then it's indeterminate, and it kind of depends on how fast it approaches 1. And so you can have 1 to the infinity that has a wildly changing answers. Like this one was a 1 to the infinity, and we got e to the 6. The other one is a 1 to the infinity, we get e to the 12. So we get wildly different answers for 1 to the infinity. We can create something that converges to any number we want. So 1 to the infinity could converge to any imaginable number. But the key is that it's called an indeterminate form, and we say the indeterminate form is 1 to the infinity, but we don't mean 1 to the infinity. We mean a number that's getting close to 1 raised to the infinity. But that's our shorthand notation. That's what we write it as 1 to the infinity as the indeterminate form. Yeah, so yeah, very good question. So let's do a little squeeze theorem. So let's do the inverse tangent one because we do this one because we see inverse tangent all the time. So when you look at this, when you take the limit of a fraction, you can take the limit at the top, the limit at the bottom. Right? The limit distributes, if you will. And the limit at the top we know is pi over 2. The limit at the bottom is infinity. So this one is actually, we don't even actually really have to squeeze theorem this one, because we know what the limit of inverse tangent is. Right? We know the limit of inverse tangent is pi over 2. We've already shown that. So this one, we really don't need to use squeeze theorem. Whereas this one, when n goes to infinity, what happens to sine? The limit of sine as n goes to infinity? is, it's not 1 because, doesn't sine oscillate?
Yeah.
So all we can say about the limit of sine as n goes to infinity is that it doesn't exist because it oscillates. This one does have a limit at infinity, so it's not,
Oh, right.
right? Arctangent approaches pi over 2. So this one has a limit, so you really don't need the squeeze theorem here. This one doesn't have a limit, so you have to use squeeze theorem. But regardless, if the numerator is a bounded function, we can use the squeeze theorem. Now, the idea with squeeze theorem is fairly straightforward in concept. We are thinking about part of the expression as being a bounded function. So that's the bound on inverse tangent. We know that it's strict inequality is less than, but it's also true that it's less than or equal to. A lot of people prefer the less than or equal to because what's about to happen. So we have that, and then we're going to divide everything by 4n. So we're going to create what we want in the middle. So we start with our bounded function, then we divide by whatever we need to divide by to get to the expression in parentheses, or brackets, braces. Now we take the limit of everything. So now we take the limit as n goes to infinity of the left side, of the middle, and the right side. And what we notice is that the left side and the right side as n goes to infinity, those approach the same value. So both the left side and the right side have a constant in the numerator and a function in the denominator that's blowing up to infinity, so the fractions are shrinking to 0. So we have this situation. So 0 to 0. And so that allows us to conclude that the limit of the middle is, in fact, also 0. So that's how a squeeze theorem works. And now again, in this particular case, this limit of the numerator is a constant and the limit of the denominator is going to infinity, so you could bypass squeeze theorem here. With sine, though, you wouldn't be able to do it. You would have to do this one, you would have to do squeeze theorem. So we would start with that, divide everything by 2n, take the limit, and the limit on the two ends are both 0. So then the limit in the middle is 0. So if you divide each of these by 2n, now when you take the limit, this goes to 0, this goes to 0, which forces this one must go to 0 also. So the limit of sine n over 2n must be 0. All right, let's try one of these recursive ones. So find the first 4 terms of the following recursive sequence and then find the limit of the sequence. They've given us the very first term. They have already given us -6. With recursive, you have to have a starting point. You need to be given a place to start, and then you have to be given a formula to get to the next term. So here, -6 is our first term. We plug it back in there. Our next term is equal to 0. Then we plug 0 in here, and our next term, oh. What is our next term?
6.
Square root of 6, yeah. Yeah, the pattern's a little different than I was thinking it might be at first. And then you start saying, oh, this is actually kind of a funky looking thing. Everybody seeing how this is progressing?
Horribly.
Right? So that's being put into here, so that we have that, etc. How many terms is it? Let's stop. First 4, okay, let's stop. That's enough. All right, so we have those terms.
I hate it.
Now, it says to find the limit of the sequence. So we had a theorem that said every bounded monotonic sequence converges. So in other words, if you have a sequence that's decreasing and it's bounded below, so there's a floor, if it's decreasing and it's bounded below, then there has to be a limit. If the sequence is increasing and it's bounded above, so there's a ceiling, there has to be a limit. With this one, do you see that it's bounded below by 0 or bounded above by, let me think about this. What is it bounded above by? Ugh. Well, it's certainly bounded below by -6, right? Never goes more negative than that. So the question then is this bounded above? And so usually what we would do is look at some empirical data, we type it into our calculator and start seeing, and if we suspect that it's bounded, then the following technique works. So the following technique only works if you're really darn sure that it converges. Now this one says, find the limit of the sequence. So they're basically telling us that it in fact is bounded above, find the limit of it. So here's what we do. So we take this formula and we are going to take the limit of both sides as n goes to infinity. So we take the limit of the left as n goes to infinity. We take the limit of the right as n goes to infinity. And what we are basically going to do in terms of our perspective is treat these as if they are different sequences. So the a sub n sequence is right there. We're going to treat this as a sequence all by itself. It's a separate sequence, and when n starts at 0, this sequence would start at that 0. So this sequence is going to have one fewer terms. So the sequence a sub n plus 1, n starts at 0, so the first term of this sequence is this a sub 1, which is the second term of this sequence when n is 1. So these two sequences have the same tails, they just differ in the beginning. This sequence has one extra term. We know that when you take a limit at infinity, the leading terms don't matter. So both of those have the same limit. So we are going to assume that the limit as n goes to infinity of a sub n, we are going to assume that that is in fact L. So somehow we're pretty convinced that this converges because we've looked at data. We're going to call that limit L. So when we do this, we end up with an algebra equation. The limit of this is just the square root of 6 plus L. Again, the square root function is continuous, and the limit can pass through continuous functions. So it can go to the inside. The limit of 6 is 6. The limit of a sub n is L because that's what we're assuming. Now we just have to solve this for L. So we move everything to one side and factor. Factor this into L minus 3, L plus 2 equals 0. So this tells us L is -2 or 3. When we look at our sequence, these are all positive. So -2 is extraneous. That has no relative meaning here. And what it tells us is that this sequence must converge to 3. So this converges to 3 as n goes to infinity. So that is going to be the limit of the sequence. So recursive sequences. Again, we don't see those a ton in algebra, or in, well, I shouldn't say algebra. In calculus, we don't see those a ton. Usually our sequences are given to us as functions. So 1 over x, or whatever. You know, we usually use a formula as opposed to this recursive thing. Most functions are just, most sequences are going to be given to us like these, right, in here. These are all functions, right? The sequence of these terms are given to us with functions. So that's going to be much more common. Just hammer out these, then we'll take our break. These should all look like geometric series. Or if you just zoomed in on the sequence, geometric sequences. And that's because the k, the index, is up in the exponent position everywhere. That's what we mean by geometric. Geometric, the k is up in the exponent position. But these are not in our standard arc form. When we have a geometric series, this is sort of the form that we think of, that arc form. The key component of this being that the exponent is nothing more than k. It's not 2k, it's not negative k, it's k. So to put this in our geometric form, where we know that if the absolute value of r is less than 1, we get convergence. And if the absolute value of r is greater than or equal to 1, then we get divergence. So we want to rewrite these so that they're in a transport, into that standard form where it's transparent. So here the key is going to be that we're going to write this as 3 to the negative 2 to the k. 3 to the negative 2 is 1/9. Does that one converge or diverge? So the r value here is 1/9. That's less than 1, so therefore we have convergence. So make sure you write down the r value. As soon as you write r equals, then I know you know it's a geometric series. And then you compare it to 1, less than 1 converge, greater than 1 diverge. This one, same idea. The negative 2 is going to be implemented. So 1/4 of the negative 2 is going to be, we flip it to get rid of the negative, so 4 over 1, which is 4. 4 squared is 16. So this one will be rewritten as 16. I guess we don't need parentheses. That will be 16 to the k. Starts at 0. And what is the r value here? 16 is bigger than 1, therefore it diverges.
Now when it says evaluate, if it does converge, do you want us to get the number?
If it says evaluate, yes. If it says
One
evaluate, yeah, good point. Kind of rushing through these because it's time for break. We'll find the evaluation right after break. We'll just do the converge diverge piece first. Yeah, if it says evaluate, you want to find the actual sum of the series. So this one, that negative sign right there, does that have any, does the exponent impact that minus sign at all? No, because that minus sign is not wrapped up in parentheses. So that minus sign is completely independent of the 2 to the k minus 3. So I'm going to pull that minus sign all the way out to the front. So that minus comes out. This is going to be 2 to the k multiplied by 2 to the negative 3. So once again, we want the exponent to be just k. And this is going to be 3 to the k times 3 to the 1. So we're getting close. We've peeled away some of this extra stuff that's happening to the exponent. These constants can come out to the front. 2 to the negative 3 is 1 over 2 to the 3, which is an 1/8, times a 1/3 is a 24th. So now we're sitting on that. All right, 2 to the k over 3 to the k, we can write it like that. The r value here is 2/3, which is less than 1, therefore converge. So let's take our break now, and then we'll figure out what these each converge to when we get back. But if you have questions, let me know, and I can help you out. Part of these geometric series. So, like Erica pointed out, it did say evaluate, which means find the sum of. So we found that each of these three either diverged or converged, and the two that converged, let's go ahead and find what the sum of the series is. So we remember that for an infinite geometric series, S is equal to A over 1 minus R. So that is our formula. And when we look over here, we saw that R was 1/9. What is A for this series?
1.
1. So we find the initial value, which is also called A, by plugging in the initial index. So that's 1. So we have 1 over 1 minus a ninth. And if you multiply everything through by 9, we will get that the sum of this series is 9/8. Question?
Well, for the last one, would the -1/24 just be A?
So, yes, we can think of it in two different ways on this one. We can think of this as a constant multiplier, and we can say that the sum is going to be -1/24, so that's that constant multiplier, and then do our, over here, focus on the series part of it. So if we do that, if we just think of this as a constant in front, then we come over here and we would say for the series part of it, this part of it, A is going to be 1 because if we plug in 0, and so we would have that. Now you could also imagine pushing this to the inside and calling that A. Either one would work fine, it doesn't matter. You can think of that -1/24 as a constant out in front, and then do the series piece, so just looking at this series, R is 2/3, and when you plug in a 0 there, you would get 1 for the first term of the series. So either of those will work totally fine. And then here, 1 minus 2/3 is 1/3, and if you flip 1/3, you get 3. And so this series will have a value of -1/8. That'll be the sum of the series. Now, how about this middle one that diverges, Danny?
Will we have any finite geometric series on the test?
No.
Okay.
Yeah. No. Yeah, that's a good question because the formula
Yeah, I
for the
just don't
finite
remember the form.
is a little harder. It's a little harder than the infinite ones. Yeah, we'll focus on the infinite ones.
All right.
So looking at that divergent series here, this does have a first term and it does have a common ratio. Just remember that if you already decided it diverged, you could find an S, but it's not really the sum of the series. The series diverges, it doesn't have a sum. But you could calculate S and and I said 0 here, I should have said A is 1. A is 1. You know, you could do this kind of thing and get -1/15. That is meaningless. That is not the sum of the series. Okay? So if the series diverges, it diverges. You don't have to go find an S. That S is meaningless for a divergent series. So because it diverges, it doesn't have a sum. So, oh, did I bring my phone back? Make sure it's off.
So real quick for the
Yeah.
last one, are you gonna like ask us for A and R? So is there a way like you want us to put that A as 1, or do you want us to put that A as -1/24?
Either way is fine.
Okay.
Either way is fine. Yeah, if you can imagine this on the inside, that's totally fine. Because this is just a constant, so it could be inside and it would be your A. Yeah, either way is fine. Either way. Whatever makes more sense to you. Whatever way makes it easiest. All right, so this series is a telescoping series. It doesn't look like it right now. Right? When we have a telescoping series, we imagine the parentheses with 2 terms and a minus in between. So we have to do some work to make this into a telescoping series. And so what we have to do is factor. So we're going to factor this denominator into k plus 1 and k plus 3. We have that. And then we have to use PFD, partial fraction decomposition. This is going to turn into A over k plus 1 plus B over k plus 3. this leads us to our PFD equation. So this part over here, we multiply both sides by the denominator on the left, and we end up with this so-called PFD equation. So there's our PFD equation. And then we find A and B. And the way we've been doing it is with convenient values. So if we let k equal -3, that's going to give us our b value of -1. So if we plug in -3 for k here, we get 0. And if we plug in -3 for k there, we get -2 times b. And then our second convenient value, k equals -1, plug that in here and we get 2a. And if we plug in -1 in the second term, we get 0. So now we've got our setup here. So we have the series. Now it's going to look like a telescoping series. K starts at 0. And we are going to have a over k plus 1. So 1 over k plus 1 minus 1 over k plus 3. So now we've got a telescoping series. What we know about telescoping series is that we have to find S sub n. S sub n means the sum of the first n terms. And so it's helpful down below to have k values and a counter, like number. You can call it n or you can call it a number, whatever you want. So the very first term is when k is 0. So if we plug in k equals 0 here, we are going to get 1 over 1 minus 1 over 3. So that's going to be the first term. The first term corresponds to a k value of 0. All right. Now we're going to go to our second term, which is going to correspond to a k value of 1. So we plug in a 1 and we get 1/2 minus 1/4. And then we're going to go to our third term, which corresponds to a k value of 2. So plug in a 2 and we get 1/3 minus 1/5. We'll go one more term here. So the fourth term will correspond to a k value of 3. So plugging in a 3. We've got that. So we've got our first 4 non-zero terms. We need to get out to the nth term. So the nth term, the number of terms being n, is here. So we want the number of terms, we want to end at n. Now we have to see the pattern to get to the corresponding k values, and the pattern is that we subtract 1. So those are the k values that will generate term number n minus 1 and term number n. So let's do it. So we're going to plug in n minus 2 right here. N minus 2 plus 1 is n minus 1. So we're going to have 1 over n minus 1 minus 1 over, plug in n minus 2 here. N minus 2, if you add 3, you're going to get n plus 1. Plus, now we plug in n minus 1, so we're going to get 1 over n minus 1 over n plus 2. So we're plugging in n minus 1 here, plugging n minus 1 there. So that is S sub n, sum of the first n terms. Now we figure out the cancellation pattern. So start down here on the left. This is going to cancel with that. So the second part cancels with the first part after you skip a term. So in general, we're thinking to ourselves that second parts are canceling with first parts after a skip. So, second parts are canceling. So this is a second part. These are not second parts. These can't cancel. Right? Only second parts are canceling. This second part will cancel with something over here after we skip that term. This is the second part, and this is going to cancel with something that's in here also. So going left to right, second parts are canceling. If we change our perspective and we start coming forward, we see that when we're coming forward, the first part is canceling with something in front of it. This term here, the first part is canceling with something in front of it. One thing in our mind is that we have two terms that are sticking around, so we need to have two terms that are sticking around on the other end. So second parts canceled going this way, first parts are going to cancel going this way. So those two things are going to cancel with stuff in the middle. These are going to be the two pieces, the two parts that persist, that don't cancel with anything. So this tells us then that in a shorthand notation for our S sub n is that plus that minus that minus that. So there is S sub n. And you could write that as 3 over 2 for the sum of those two things. And then what is the limit of S sub n as n goes to infinity?
3/2.
3/2. So that is the sum of the series. It's the limit of S sub n as n goes to infinity. Yeah?
Remind me, because I remember we were talking about this before. How do you know if it is going to be 0, 1, 2, and 3 for k, and then n minus 2, n minus 1, but then when it comes to for n, it's n minus 1 and then n?
So the number of terms is just counting. 1, 2, 3, and we want n terms because that's what this means. So S sub n means count until you get to n.
Okay.
So this one down here is just pure counting. 1, 2, 3, 4, and you're going to stop at n. Right before n is n minus 1. Right before n minus 1 is n minus 2. You know, so if you put in an n minus 2, it would be here.
Right.
And you know, so and then the series though is built by plugging in k's. So we need to ask ourselves, to get to the first term, what do we plug in for k? Well, the first term is based on whatever this starts at.
Right.
If this started at 6, then this k would be 6. And this k would be 7. And this k would be 8. So these k values go up by 1, just like the n's go up by 1, but they start somewhere different. So we just have to see the pattern to establish these two. And the pattern is that you subtract 1. You subtract 1. You subtract 1. You subtract 1. So over here we say, oh, if we take n minus 1 and we subtract 1, n minus 1 is n minus 2. Same thing here. N minus 1 is n minus 1.
Right, okay.
So we establish that pattern over here, and then we do the same at the end. So the term counter is always 1 to n. And then, so if this did start at, let's say this started at 4. Then this would be 5. Then this would be 6. Then this would be 7. What would this one be?
N minus.
So what is our pattern here? How do we get from there all the way up to here?
Oh, it has to be 3.
So we added 3. So to get from 2 up to here, we added 3. Here we added 3. So what is this one going to be? If you add 3 to this?
That's going to be n.
Yep. And over here, if you add 3,
N plus 3.
n plus 3. Yep. So you always establish that pattern in front and then do it over there at the end. But the counter is always going to be 1 to n. And then we have to figure out what the corresponding k's are. And those are the corresponding k's. Okay, divergence test. So the divergence test cannot find convergence. The divergence test can find divergence, or otherwise it's inconclusive. So when we look at this first one here, we ask ourselves, what is the limit as k goes to infinity of that? All right. Well, that's a L'Hopital, right? That's infinity over infinity. It's indeterminate. Infinity over infinity. And so we can apply L'Hopital's rule. L'Hopital's rule says take the limit of the derivatives. So in the numerator, we take the derivative. In the denominator, we take the derivative. And the denominator's derivative, we have to use the chain rule. So we get that. 1 over the inside times the derivative of the inside. So let's simplify. The denominator just becomes 1 over k. The numerator becomes 1 over 2 root k. So overall, we end up with k in the numerator, 1 over root k in the denominator, 1 over 2 root k in the denominator. Or I said that wrong. We end up with, when we flip the k, we end up with k in the numerator and 2 root k in the denominator. And then we simplify. Root k goes into k, root k times. So we have that. K is root k times root k. So root k goes, or you can subtract the exponents, k to the 1 over k to the half is k to the half. And then what's that limit? Infinity. And the divergence test says, what then?
Therefore, it diverges.
This diverges because this is not equal to 0. If that is not equal to 0, the series must diverge. The only way a series can converge is if you're adding numbers that are close to 0 in the end. All right, so that diverges. This one, take the limit. As k goes to infinity, we have square root of k over k cubed plus 1. Again, this is L'Hopital. So we have infinity over infinity. So we take the derivative of the top, the derivative of the bottom, so that's 1/2 k to the minus 1/2. Derivative down here is 3k squared. So this will be the limit of 1/6. And now the k's. Where do we end up with? Let's see, we end up with 1 over k to the 3/2. Or no, 1 over k to the 5/2, actually. Because this 1/2 comes down, so you have k to the 2 times k to the half, which is 2 to the k to the 2 plus 1/2, which is 5/2. And what is the limit of this as k goes to infinity? 0? Because the k is in the bottom, it's blowing up, so the fractions are shrinking to 0. This tells us what then? Inconclusive. All right, so it says it might converge or it might diverge. We don't know. We have to go do a test.
I think that's a negative half, but I don't know, it's not, never mind. We're good.
Good?
It doesn't matter anyway. But.
So, yeah, so when we took this derivative here, this is 1/2 k to the minus 1/2. When that comes out, it becomes positive 2 plus
No,
1/2.
you're right. You're
It
fine.
makes sense?
Yeah.
Okay, good. All right, yeah.
Instead of doing all the work right there, can we just use the rule where the power is lower in the bottom, so it equals 0 when you take a limit?
Are you looking right here?
Yeah.
You said the power is lower in the bottom?
Yeah, so it equals 0.
What do you mean?
Higher in the bottom.
Bottom.
Higher in the bottom, sorry.
Okay, all right.
It's lower on the top, higher on the bottom.
Yeah. So that, yeah, absolutely. You can do that. This is a little tricky just because it's a k to the 1/2. So, but what you're thinking of is dividing by the highest power of k, which yes, absolutely. Yeah. If you establish that the denominator's power is greater than the numerator, then the limit's going to be 0. Yeah, that's for sure. So you can do that. Ratio test. Now, in order to do the ratio test, you have to have this in summation notation. I'm not going to ask you to do that on the test, so let's pass on that one. So we have this. So use the root test to determine convergence here. So remember, root, ratio, geometric series. Those are 3 siblings, triplets. R less than 1 converge, R greater than 1 diverge, and then for root and ratio, R equals 1 inconclusive. So, root, ratio, and geometric series, triplets. Less than 1 converge, greater than 1 diverge. So the root test says, let's take the limit as k goes to infinity of the kth root of the absolute value of a sub k. So we're just going to put the a sub k in here, and if we had a switch, we would turn it off because we're taking the absolute value. All right, so we're doing the kth root of all that, kth root of a sub k. Well, the kth root means that you're going to divide out a k from this exponent position. And so we're going to be left with k over k plus 5. And we divide out a k, so we get to the 4k. Now, Peyton's question is very pertinent here. This question does not say anything about using the log limit process. So here you could use the shortcut. Here you could use the shortcut because it doesn't ask you to use the log limit process. So here we would flip the base. And if you flip the base, you turn the exponent to the other side. And then we would distribute the k, so we have 1 plus 5 over k, to the negative 4k. So this is A, this is B, so this is going to be e to the power of negative 20.
Now, if you kept going, though, can you take the kth root again, or no?
No.
Okay.
Yeah, so with the root test, you can only do that k thing one time. One time. So do we have convergence or divergence?
Convergence.
That number, e to the negative 20, is less than 1. You could write it as that with a positive exponent. So you indicate that this is less than 1, therefore we have convergence. So root, ratio, geometric series, the triplets. Less than 1, converge. Greater than 1, diverge. Comparison test. Okay, so we're looking at that thing. When we use the comparison test, we have to build a series, and we usually call it B sub k. The series that we're analyzing is called A sub k. And we construct B sub k typically by getting rid of parts of A sub k that are insignificant, or at least less significant. And when we look at this, the fourth root of k goes to infinity very slowly. It's a bird wing. k goes to infinity much faster than the fourth root of k. So compared to each other, the 5k dominates the fourth root of k. So what our hunch would be to use that as your b sub k. Now you might also make the argument that the 5 is insignificant and you could just go 1 over k. And that's true. But what we have seen a couple of times is that if you ditch this extra multiplier, sometimes you can't make the inequality work. So I'm going to leave that in here. So the corresponding series here, 1 over 5k, that's really 1/5 times the series 1 over k. And does that diverge or converge?
Diverge.
And that diverges because it is,
Because the power is 1, then in that case, it will diverge.
yes. So if the power is down here in the denominator, so this is a p series, so here we will have convergence if p is greater than 1. So you can say that this diverges because of multiple ways. So you can first say that p is 1, which implies divergence. Or you could say p is 1, which implies the harmonic series. And we know, we've done it enough now, that we know that the harmonic diverges. So you can say either of those things. So, we come back up here with the comparison test. We are comparing the a sub k with the b sub k. And the question is, do we want the a sub k, the series that we're analyzing, do we want it to be greater than or less than the b sub k, the series that we built that diverges?
We want 1 over 5. We want b sub k to be less than a sub k.
Do we agree with that? So if the b sub k series diverges, the a sub k series will also diverge if it's bigger. If the a's are bigger than the b's, the a's must diverge because bigger than diverging will diverge. So we know the b's diverge. So if we can show that, then the a's have to diverge. A series that's greater than diverging must also diverge. A series that's less than converging must also converge. But less than diverging is inconclusive and greater than converging is inconclusive. So that's what we want to show. So we take our a, more correctly our a sub k, and we don't know, but if we can show that this is true, then we are good. So we're going to cross multiply. So 5k on the left. On the right, we get 5k minus the fourth root of k. Subtract off the 5k's. So we get that. And so here's where you want to just make note that if you didn't have the 5 in here, these wouldn't subtract away neatly. You'd have a 5k on one side and a k on the other, and then you wouldn't be able to show the inequality the way we want to. And now, is this inequality true or false? True. So this is true. On the right, you have a negative number. 0 is bigger than any negative number. So that is true. So our conclusion is, therefore, the original series diverges. Therefore, both series diverge. So the a sub k series must diverge because the b sub k series diverges. So that is the comparison test. Alternating series. Okay, in your head, think about A, whether both series converge, regular convergence with the alternating series test. In your mind, when you think alternating series test, there's two things. The terms decrease, and the limit is 0. we did it in the opposite order. We said, hey, take the limit first because who cares what happens to the subsequent terms? If the limit's not 0, you know it diverges. That's the divergence test. You know it diverges if the limit's not 0. So think in your head. A, is the limit 0 for both of these? B, are the terms decreasing if you ignore the switch? And then conditional or absolute. So remember that absolute convergence means that the absolute values converge. That if you take away the switch, you still get convergence. Normally, when you have convergence and you have an alternating series, the minuses are helping you out, right? They're subtracting a little bit. You're adding these numbers together and they're doing a little bit of subtraction, so they're helping. But sometimes you don't need that help. Then it's absolutely convergent. So think about that for a moment. You should be recognizing, without the switch, that both of these are p-series. Okay, so top series. Does it convert regular convergence with the alternating series test?
Top one, no.
So the alternating series test has two pieces. What is the limit of 1 over k to the 3 halves as k goes to infinity? 0. So that part checks. The other part of the alternating series test says, okay, ignore that. Do the terms get smaller? So if you plug in a k plus 1 there, is that smaller than if you just have the k there? And the answer is yes.
So we don't treat that as a power series when we're trying to find the limit as k approaches 0?
We're taking the limit as k goes to infinity.
Gotcha.
So limit as k goes to infinity, the limit of that is 0, which is the first part of the alternating series test. So that's the divergence test being inconclusive because the limit is 0. But then if your k's are in the denominator and there's only a constant in the numerator, the terms are getting smaller. Right? If that's a 5 and then it turns into a 6 and then turns into a 7, the denominators are getting bigger, so the fractions are getting smaller. So this does pass the alternating series test. So this converges by AST. So the limit of 1, and remember with AST, we take the limit of a sub k, and this is a sub k for an alternating series. You don't use the switch. And then the second part, we want to show that the terms are getting smaller. So as we go out in the series, we want that to be true. So we look at this comparison. So that's what we want to show. We do our cross multiplication, and that gives us k plus 1 to the 3 halves greater than k to the 3 halves. We can raise both sides to the 2/3 power. We get k plus 1 greater than k, which tells us 1 greater than 0, which is true. So therefore converge. So that's regular old convergence. And anytime we have an alternating series that converges, we then ask the deeper question. Is the convergence conditional or absolute? So that now that we know it converges, then we come up here and we say, okay, well, what about the series where there's no switch, where everything is positive? So then we have that series. And the question is, does that series converge or diverge? And what kind of series is it? So that's a p series, and p is equal to 3 halves. Which is bigger than 1, which is
Convergence.
Convergence for a p-series. So easy to goof up your triplets with the p-series, because right, the p-series is the stepchild. It's opposite. For the triplets, geometric series, ratio test, root test are less than 1 converge. But for the oddball, for the p-series, greater than 1 converges. Because the P series is looking in the denominator. And in the denominator, when the exponent is bigger than 1, you have convergence. Okay, so that's convergence. So what does this tell us about the overall convergence? What type is it?
Absolutely.
So it's going to be absolute convergence because it doesn't matter whether you have minus signs. If you have the minus signs, you get regular convergence. If you take away the minus signs, you have convergence still. So it's absolute convergence because the series of absolute values converges. Now look at this one. This one's a little different. This one, we still have the AST giving us convergence. Right? That limit is 0. Denominator gets infinitely big. Numerator is a constant, so the terms are going to 0. And then here we would want to show that the terms are decreasing, and we know they are. Because if the k is in the denominator, the bigger k gets, the smaller the fraction gets. So the a sub k, and then if we add 1 to the k, the denominator is getting bigger. We know the fractions are going to get smaller, but we have to show the math. So we do the cross multiplication. We raise both sides to the 3/2 power. We subtract k. That's true. So that being true, therefore we have regular old convergence. This alternating series converges. This alternating series, if you were to look at a picture of it, the partial sums are going to be oscillating around whatever the limit of the series is, whatever the value of the series is. But then we ask the deeper question. Now that we know that, then we say, well, what if we take away the minuses? So what if we take away the switch? We ditch the switch. This is a P series with P equal to 2/3.
That's less than 1, so it diverges.
Less than 1, therefore it diverges. P series.
So that's a conditional convergence.
What he said. So therefore we have conditional convergence. Because the minus signs created a divergent series, but if you take away the minus signs, you have let me say that again. If you have the minuses, you get a convergent series, but if you take the minuses away, you have a divergent series. So the series converges conditionally because you need the minuses. If you take the minuses away, you have divergence. So therefore, the series converges conditionally. So you should be able to see that before you even start any writing. When you're looking at this, first in your mind, you should be thinking, okay, the k's are in the bottom. That means the terms are going to go to 0, and they are going to decrease to 0. But then you say to yourself, wait, that's a P series. Bigger than 1 converge, less than 1 diverge. The opposite of our triplets, the opposite of the geometric series root and ratio test. So the P series is the oddball. It's the stepchild. Oh, poor stepchildren. Many of us are stepchildren. Okay, radius of convergence. We now have upped the ante, and we don't just have series of numbers, we have series of powers of x. So these guys are polynomials that go on forever and ever and ever and ever. And it doesn't matter where they start, k1, k a million, k whatever. Some non-negative number, it doesn't matter where it starts. We know that convergence is based on the tails. So this says, find the radius of convergence. We've had 2 techniques, ratio test or root test. Those are the only 2 that we use for power series. We see this root, this power out here, which sort of says, hey, use the root test. Let's get rid of the power. So let's do that. So we are going to take the kth root. We're going to take the limit of the kth root of the absolute value of 8kx to the k. As k goes to infinity. So the kth root of blah blah to the k, those k's undo each other. So we end up with the kth root, that cancels, so we end up with the absolute value of 8kx.
Wouldn't it just be absolute value of x?
And so now we say to ourselves, 8's always positive, k's always positive, so that does not need to be in the absolute value sign. So we're going to say limit of 8k absolute value of x. This limit is as k goes to infinity. Does x depend on k? No, there's no k in the x. The x is the x. If k goes to 5 or 100 or 1,000,000, it doesn't change the x. So we can rewrite this as 8 absolute value of x, limit of k as k goes to infinity. Right? The 8 and the x don't depend on the k, so they can come out to the front like constants do. And what is this limit? Infinity. Okay. So this is one of the outlier cases when we have a limit that is infinity, or regardless of what we get with the limit, whatever we get here, we have to say, when is that limit less than 1? Root, ratio, geometric series, less than 1. When is that less than 1? Never. No, it's infinity. That's never less than 1. This is never less than 1. Therefore, the radius of convergence is 0. Therefore, the interval of convergence is what?
0.
0. Because that is the center of this series. Right? That series is centered at 0. It doesn't say x minus 5 to the k. It doesn't say x plus 3 to the k. Right? That series is centered at 0. So a is 0. Centered at 0. Every series converges at its center. If you plug in the center, you get a bunch of zeros everywhere. So adding up a bunch of zeros converges. So every series converges at its center. If this thing is never less than 1, then you only have that very limited convergence. It only converges at its center. What is the center of this series?
0.
0, right? It's just x. If it's x minus 2, the center would be 2. If it's x minus 5, the center would be 5. If it's x plus 3, the center would be negative 3. But this is just x. So this center is 0 also. This one, what test should we use? Root or ratio?
Ratio.
Yeah, we see the factorial. As soon as you see that factorial, you want to go ratio. So limit as k goes to a lot. And we want to find a sub k plus 1 absolute value over a sub k. So first we're going to plug in k plus 1 for the k. And we need the absolute value, remember, because we have an x. X can be any number. Negative, positive, who knows. So we need the absolute value. So we have 2x to the k plus 1 over k plus 1 factorial. Don't need the absolute value down there. K plus 1 factorial is always positive. K is always positive. So there is a sub k plus 1. Now we divide by a sub k. A sub k is a fraction, so we multiply by its reciprocal. So we have a k factorial divided by absolute value 2x to the k. So let's think about this carefully. Let's sort of stack things in a convenient way, and then we'll talk about simplification. So first off, I am going to say to myself, well, that 2 does not need to have an absolute value. That 2 is positive, so it's going to come out. Same thing down here. I'm going to group the x's and put the x's under the x's. Same thing, right? the 2 is positive, it can factor to the front of that absolute value. And then over here, let's stack the factorials. We have k factorial, and we know that k plus 1 factorial is right like that, right? K plus 1 factorial is k plus 1 times k factorial. Now we see some cancellation. The 2's cancel, the k factorials cancel. The x's simplify. Let's see, we have how many x's left? Well, k plus 1 minus k, we just have absolute value of x left in the numerator. There's one extra x up top. K of them cancel. And we have a k plus 1 in the denominator. Once again, the x does not depend on k. If it doesn't depend on k, that means it can be treated like a constant. It can factor to the front. And this limit is 0.
Oh, sorry, 0.
0. The denominator is going to infinity, so the fractions go to 0. Everyone agree? We're going to see it as 0. And then we ask ourselves, root ratio, geometric series, when is it less than 1? Always. So we ask ourselves, when is this less than 1? So up here, less than 1, never. If it's never less than 1, the only convergence is at the center. Here, this less than 1 is always, right? That's always true, always factorial. Always true. Always true. So therefore, what is R, the radius of convergence?
Infinity?
Infinity. If it's always true, that means any x you plug in, you're going to have a limit that's less than 1, regardless of what the x is. If you put x equals 10,000 right here, well, 10,000 times 0 is still 0. This is 0 no matter what x you put in. So there is our radius of convergence, and the corresponding interval of convergence would be that. Okay, so those are our two extreme cases. Ooh. No, I don't want to do that right now. So now let's do the middle of the road case, which takes more work because we're going to have to test endpoints. The middle of the road case ain't so middle of the road. So we are going to use the ratio test here. So the limit as k goes to infinity of absolute value of a sub k plus 1 divided by the absolute value of a sub k. So the ratio of consecutive terms. So first we're going to replace the k with k plus 1. We're going to have an absolute value. When that k gets replaced with k plus 1, you get 2k plus 2 plus 1, which is 2k plus 3. Divided by 5 to the k. If you replace that k with k plus 1 minus 1 is k. Okay, so there's our a sub k plus 1. Now we take our a sub k, it's in the denominator, it's a fraction, we flip it. So we get 5 to the k minus 1 in the numerator, and we get absolute x to the 2k plus 1 in the denominator. Let's think about the 5s first. Are there more 5s in the numerator or more 5s in the denominator? Denominator. There's one extra 5 downtown. So we're going to put 1 5 down there. 1 extra 5. How about the x's? Are there more in the top or the bottom? Top? How many more?
2.
2. 2. Right? There's a bunch of x's up here, there's a bunch of x's down there, but there's exactly 2 more x's up here. 2x's, x squared. Do not need absolute value sign around that. That's positive. X is squared. So we have that. What is the limit of this?
Can you just, I guess, go over the process of the whole multiplication of a limit? Because you get the x
In
squared-
here?
Yeah, you get the x squared over 5, but I don't really understand how you get that.
So do you get the 5 part?
Yeah, that they cancel out.
Yeah, so like if you went back to algebra, you would say, hey, we've got a fraction of powers of 5. We're going to take the upper exponent and subtract off the lower exponent. And this would give us 5 to the negative 1, which is 1/5.
Okay.
Does that make sense?
Yeah.
Or you can think about like if you had 10 5s in the bottom and 9 5s in the top, you'd end up with 1 in the bottom. Which is what we have, right? We have 1, this is 1 less in the numerator. So we have 1 more in the denominator. So we're going to end up with just 1 in the denominator.
Okay, and then the
And then with-
x's, you're just subtracting the 1 from the 3, and that's getting you the x squared, right? Because the 2k's cancel out.
So same idea, we have a power of x top and bottom. We take the upper exponent and we subtract off the lower exponent. The 2k's disappear and we end up with x squared, right? 2k minus 2k is 0, 3 minus 1 is 2. So, or you can think of it a little more conceptually that there's a bunch of x's being multiplied here, there's a bunch of x's being multiplied here, and there's exactly 2 more. Right? You add 2 to the 1 and you get a 3, so there's 2 more in the top. So you can do it with that, with the algebra rules of exponents, upper exponent minus the lower exponent, or you can think a little bit more conceptually that there's 2 more x's in the top.
Okay, so those are kind of the fundamental rules when you're doing those.
Yeah, we're always thinking about how many 5s or how many x's in each place, and then a bunch of them cancel and there's usually 1 or 2 left over. In this case, there's 1 5 and 2 x's. And how about the limit of this? This limit is as k goes to infinity.
1/5.
Is there a k in there?
No. So it's 1/5.
What happened to the x's?
They go to the front.
So it's part of the limit though then, right? So the limit, this is all constant, so the limit of a constant is a constant. So what you're thinking of, we could do exactly what you just suggested. We could say this. But the bottom line is that that's going to be our overall limit. Right. The overall limit is going to include the x. Right? The x is still there. Now with the other two, with those extreme cases, we get the 0 and the infinity. It doesn't matter what x is. But here the x is going to matter. Right? Because our next question is, well, when is that less than 1? In the prior 2 examples, one answer was always and one answer was never. Here it's sometimes. It depends. Right? If you plug in x equals 1, then yeah, that's less than 1. If you plug in x equals 25, then no, then it's not less than 1. Right? So some of the x's are going to give us a limit value that's under 1, but some aren't. So this is the other case. So we want to know when x squared over 5 is less than 1. That tells us that x squared has to be less than 5. And that tells us that x has to be somewhere between the square root of 5 and negative square root of 5. This tells us our radius of convergence right away. This tells us our radius of convergence is square root of 5. And it tells us the goalposts for the interval of convergence. It tells us that the left endpoint is at minus root 5, and it tells us that the right endpoint is at positive root 5, but we need to calculate the convergence at the endpoints. We don't know the convergence at the endpoints yet. So let's do the endpoints. So we're going to plug in negative root 5. So x equals negative square root of 5. So we come up to the series. We're plugging in for x negative square root 5. All right. We are going to change that up by doing the following. The negative 1 to the 2k plus 1, that's going to come to the front. So negative 2k plus 1, is that really a switch?
No.
No. Isn't it always odd? Right? 2 times k is always even, and if you add 1, you always get an odd. So that's actually going to just turn into a minus 1 times on the outside. Because that's always odd, that exponent.
What do you mean by odd?
Not even?
No matter what k is, the
Oh,
exponent always
okay.
ends up being odd.
Okay.
So if you plug in k equals 3, you get 6 plus 1, which is odd. If you plug in k equals 4, you get 8 plus 1, which is odd. So 2 times any k is even. 2 times k is even, but if you take an even and you add 1, you get an odd.
So when it's odd, you just remove the negative sign outside?
Yeah,
If it was even, would it matter?
it would just disappear. Because then it would always be positive 1. Okay, so now here, do you agree that this is 5 to the half?
Yeah.
The square root of k is 5 to the half. So 5 to the half, we have to multiply this by 1/2. 5 to the half, this is going to be k plus 1/2. And down below, we have k minus 1 as the exponent. So now we're going to do what we just did a minute ago, the upper exponent minus the lower exponent. So the k minus k cancels, and you have 1/2 minus minus 1, that's 1/2 plus 1, that's 5 to the 3/2. So this is no longer a fraction, we just have a 5 to the 3/2 here. All right, the k's are gone. The k's are going to be gone. Does this series converge or diverge?
What is the negative?
What is the limit of a sub k?
It converges.
It diverges.
So the limit of a sub k is,
Infinity.
the limit of a sub k though is, this is a sub k right here.
Yeah, there's no k's.
So yeah, so it's not.
So the limit of a sub k is this number, is
Yeah.
that no, is that limit 0?
No.
No. So you have 2 ways to think about this. So yes, it's going to diverge for sure. And so the limit of a sub k, and like you said, there's no k's, so the limit of this constant is itself, this is not equal to 0, therefore diverge. So that's the divergence test. Okay, now, let's just think in our head. We don't have time to write it all out. I can write it in my notes as after. If this was just root 5 and not minus root 5, isn't the only difference that there's no switch, or no switch that's not really a switch? Right? If we plug in root 5 and without the minus, we're going to end up with the exact same thing, except this is going to be a plus in front, and we are going to also have divergence. So our interval of convergence is going to be soft on both sides. We aren't going to include the endpoints. All right, so I will, I'll clean this one up. I'll write down the other endpoint there, and then I'll make sure that all the answers are in there for the ones that we didn't get to. And email me if you have questions on any of them.
Which series do we have to?
So the series, I put them up here on I put them at the very top. So here are the 5.
Okay.
So the exponential series, the geometric series, inverse, tan, cosine, and binomial. So those are our 5. So make sure you know those 5. And so there's some alignments here, right? The geometric series and the binomial look very similar. And then the exponential is going to be closely related to cosine. Inverse tangent is also closely related to e to the x. It's the odd powers of that factorial. All right, so I'll be looking at my emails. If any questions come up between now and Thursday, shoot me an email. I will get those worksheets graded right now. I'm going to go finish grading those. I will see you all on Thursday. The final test before the final. It's going to be great. It's going to be great. It's the penultimate test. The final is the ultimate test. I was always confused by that expression. I always thought